In the previous lesson, both conventional AM and DSB-SC still use two sidebands around the carrier. That raises an important engineering question. Do we truly need both of them? For a real valued message, the upper and lower sidebands are mirrored copies in frequency. They are shifted to opposite sides of the carrier, but they do not carry independent new information. So if bandwidth is precious, transmitting both sidebands can feel wasteful. That observation is the starting point for single sideband and vestigial sideband modulation. Single sideband, or SSB, keeps only one of those mirrored sidebands and discards the other. In practice, the carrier is usually suppressed as well. The result is powerful. The occupied bandwidth drops from about 2 times the message bandwidth to about 1 times the message bandwidth. At the same time, power is no longer spent on a duplicated spectral copy. That is why SSB became so important in narrowband voice radio and long-distance communication. Its price is higher implementation difficulty, because generating and receiving a clean single sideband is more demanding than simple AM. Vestigial sideband, or VSB, is the practical compromise. Pure SSB is efficient, but near the carrier frequency, it can be difficult to realize the ideal sharp filter that removes exactly one sideband and nothing else. This becomes especially awkward when very low message frequencies matter. VSB solves that problem by keeping one sideband almost fully while leaving a small vestige of the other. That means the bandwidth is slightly larger than SSB, but filtering and demodulation become much more practical. This is why VSB became attractive in wideband broadcast systems, such as television video transmission. Now we can compare the AM family with a clearer engineering lens. Conventional AM is easiest to receive because the carrier supports simple envelope detection, but it is poor in power efficiency. DSB-SC removes the wasted carrier power, yet still pays for two sidebands. SSB is the most bandwidth-efficient member of this family and also avoids duplicated sideband power, but it demands better oscillators, filtering, and tuning. VSB sits between SSB and DSB styles. It gives back a little efficiency so that practical filters and receivers become easier to build. So the big idea is this: AM design is a trade-off between bandwidth, power, and receiver simplicity. If simplicity matters most, conventional AM is attractive. If carrier power should be removed but bandwidth can stay the same, DSB-SC is useful. If spectrum is scarce, SSB becomes very attractive. If a pure SSB filter is too difficult, VSB offers a practical compromise. In the next lesson, we leave amplitude-based modulation and ask what changes when the information is placed into frequency or phase instead.